All right, welcome everybody to video 15, which is going to introduce this idea of a vector. Now, the objective of this video and the objective of the following two videos is to learn essentially what a vector is and their characteristics, so how we can describe and write vectors, both algebraically and geometrically. And what we'll do is we'll end up starting geometrically and then move into algebraically. How can we write an expression or talk about a vector in a better way that will help us in terms of algebraically solving problems, but we'll also be working geometrically, which you'll see in your project assessment, which will come in Thursday and Friday this week. Okay, so when we talk about a vector, vectors are kind of interesting because depending on the subject of or the application of a vector, there are actually three ways to classify a vector. The first way is the physics definition, which is a vector is defined as a path, or really it's as a ray that has magnitude and direction. So essentially a ray is a arrow, so it starts at a point and then emits from that point. And as you draw that arrow, this arrow is finite, meaning that the arrow doesn't imply that it goes on forever, but that there is a specific length to this vector. That is what the word magnitude is referring to. And then there's also a specific direction that this vector has. And so certain vectors applications are forces. You can look at them in terms of acceleration and velocity and distance, and vectors are used widely in physics and in the natural sciences, and definitely in further math classes. All right, the other way that you can define a vector is through computer science, and in computer science, a vector is an ordered list, an ordered set of items. And for example, to help kind of explain what this means is, let's say you have a house, and let me draw just a really brief house here. Now, let's say I wanted to describe this house using a vector. Well, I would use a bracket, something like this. And let's say I want to talk about it in terms of square footage, so the size of the house, compared with the price of the home. So a vector in this example, you could say square footage would be something like maybe 2,000 square feet. And the price for something like that in Atlanta could be 400,000. And so notice that when we have an ordered list and when we talk about a vector in terms of computer science, notice that the order, like where an item is, actually matters. For example, if I just had the numbers 2,000 and 400,000, like so, this is not the same thing as saying 400,000 and 2,000, because again, the top entry is square footage and the bottom entry is price. So the first option here is like what we've talked about, a 2,000 square foot home with a price of 400,000. The second vector would describe a 400,000 square foot for only $2,000, which is very, very, very different in terms of what you'd be paying for. You'd obviously want this if this was real world. But notice again that vectors aren't directly equivalent. Like you can't just mix and match where the numbers are. The numbers have a specific meaning. Now, the mathematical definition is essentially trying to do a combination of the two of these. So the idea is just to try and come up with a general definition between these two different things, so that a vector is an ordered list, but not only that, it also defines something in terms of magnitude and direction that can be used for that. So what we ended up doing is we actually define it mathematically in terms of what we can do with a vector. So for example, the way that it's defined is it's defined through the operations of scalar multiplication and vector addition. So it's all about what we can do with the vector, the operations on a vector. And this is what the video, your next video will essentially get into, that will happen on Friday, and what the project assessment will kind of get into. For now, we're actually going to just use the physics definition because it's so much easier to use and easier to visualize. And then from there, in higher math classes, you start getting into a little bit more of this general idea. When I was doing my master's was focused on matrices, which is a collection of vectors. And we looked at vectors in terms of this kind of form instead of looking at it in terms of magnitude and direction. And then we were applying this kind of addition and multiplication to that, and then analyzing those vectors and looking at different combinations and stuff like that. So at the core concept and the scope of the class that we're in, the scope that we're mostly going to stay in here is in physics, because that's what y'all are going to be really using these for if you're to take physics next year, if you have not taken it yet. This definition and what we do here will be very, very useful for when we get to that, or when you get to that in terms of that class. All right, so let's go through and actually let's really define a vector then. And we've got the definition above, but I want to draw a picture and things like that for it. So the way that I'm going to talk about a vector is I'm going to define it as a vector v that has an initial point. Actually, you know, let's say this, that has magnitude, which is the length of the vector, and direction. I say v is the path from an initial point to a terminal one. So you're going to hear me refer to vectors a lot as a path, because I think it's really easy to kind of visualize this. So again, think about it like a map, treasure map. We did this. I did this with my pre-cal classes last semester. We obviously won't be able to get to do this now, but it's why there's still Lego minifigures somewhere in the field next to the school that we couldn't find. We could create a treasure map, and your steps would essentially be vectors. So let's say, for example, this was my initial point. Let's call this P. This would then be my initial point. And I wanted to get to a terminal point. Let's say that terminal point, just to draw one, is here. Let's call this Q. Excuse me. Then the vector can be sketched as an arrow starting at the initial point P and ending at the point Q. Now, I wouldn't just draw a line like this, because notice that a vector isn't just the distance that we would walk on this path, but it's also how we're walking. So because there's a starting point and an end point, I need to draw the arrow to show where that end point is. So every vector will have an arrow on it, showing you the way that we're going to walk it, because how we define this later will be very, very, very important. All right, now we talked about how a vector is actually defined in terms of its magnitude and its direction. And so if we do not have an initial and terminal point, then what I could do is describe this vector v here in terms of its magnitude and in terms of its direction. Sorry, let's say I'll put this one step below. Now, its magnitude is going to be the length of this vector, and is actually notated using the absolute value signs, like so. You'll also notice when I notate a vector, I'm going to use an arrow essentially above my letter. Generally in textbooks and things like that, the V, your vector, is bolded, but it's really hard here when I'm writing for you to really kind of tell if it's bold or not. So I'm always going to use this arrow for it. Now the absolute values, if you think about absolute value, all that means is you're finding the distance from your number to 0. Well, for a vector, since we're looking at it as not just a number line, we're just looking at it in terms of the length or the distance that I would have to walk from point P to point Q. And so this symbol will always represent that, and it will represent the magnitude. Now the direction is the angle off of the horizontal. That's how I'm going to define this. So the direction is always going to be theta, and this is going to be measured from the horizontal, because this is what we were doing when we talked about reference angles and we were working with angles in terms of the unit circle. Now, to better keep a consistency here, and because we're going to apply mostly the physics definition, the other part that I want to make sure that we use is we're always going to be talking about the compass directions here when I talk about an angle. So are we going 45 degrees north of east? Are we going 60 degrees south of west, right? And how we use that language. Now you'll notice I've been, even right then, the words that I said was north of east and south of west. So everything, because it's measured off of the horizontal, we don't just say northeast, because when you do your angle measurement, are we talking about something in this direction? Are we describing it in terms of this rotation? Are we describing it in terms of this rotation? Both rotations can be very different, especially when your angle is something like 60 degrees. 60 degrees measured off of the horizontal is very different from 60 degrees measured from the vertical, right? And so we have to be very clear in how we're going through and measuring these. So to go ahead and create a standard, if you're looking at a compass, we know that we have our general north, south, east, and west. So I'm going to draw those lines first. All right, so I've got my east, my north, my west, and my south. If we are in the first quadrant, any angle that puts you in this quadrant is always going to be measured as north of east. Because again, the angle will be created with the horizontal, which is measured off of east. If you're in quadrant 2, this will be north of west. Because again, we're measuring it based off the horizontal. So that means if I'm in quadrant 3, this would be south of west. And then if I'm in quadrant 4, south of east. I'm going to be consistent in here, and I'm going to be looking for these descriptions as well. You cannot just tell me that your direction is 30 degrees. It needs to be 30 degrees north of east, north of west, or south of east. Because I can be 30 degrees in any one of these quadrants when I'm measuring it just in terms of the horizontal. All right, and so this is what you would see again in a physics class. So I want to kind of maintain that viewpoint and that concept. All right, so how do we find these things? All right, so now in order to find magnitude and direction, I want to teach you essentially through example 1. All right, and so example 1 says sketch the vector v that has the initial point 1, 2 and terminal point 4, 6. Then we're going to determine the following. All right, so I have my coordinates drawn out here. Now I'm going to plot my point. So I have 1, 2 is my initial value. So let's see. So 1, 1, 2. So here's my initial point. I have a terminal point of 4, 6. So 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. All right, and then I'm going to draw my vector as an arrow going to that terminal point there. And so here's my vector for v. And here's my sketch for it. Now the direction is gained by essentially drawing off of the horizontal of that initial point there. So there's my measurement for my angle. And again, I want to know this distance here. Now the technique to find the magnitude is to actually notice that I can take this and actually create a right triangle here. And this is the connection to trigonometry. Notice by forming this right triangle, by looking for the magnitude, I'm essentially going through and saying, what is the hypotenuse? Now, because we're on a grid and because we're on a graph, we can actually find the sides of this triangle. This would be 1, 2, 3, and this would be 1, 2, 3, 4. Essentially my rise over run going from my initial point to my terminal. And so we can find the magnitude by Pythagorean. All right, and that's actually going to establish our first main definition for magnitude. It's that the magnitude is equal to, in this case, Pythagorean. So that would be 3 squared plus 4 squared, and I'm taking the square root of that. So this would be equal to 9 plus 16, which is the square root of 25, or just 5. And this makes sense in terms of a distance or a magnitude here because it's a 3, 4, 5 triangle. So when I rise up 4 and run 3, that's giving me my measurement there. Now to find my direction, I need to go through and find my angle. Now, when I find my angle, notice in terms of the given information, the only thing that I know for sure is that this side is 4 and this side is 3. And under that, I'm trying to find this angle. And so in a right triangle, there's a specific relationship involving an angle with the opposite side and the adjacent side, and that is tangent. So in other words, I know that there is the relationship, the tangent of this direction here, tangent of my angle, has to be equal to 4 over 3. And we talked about when we did inverse trig. If you have not seen that video, again, I would encourage you to go back and watch that. I can use a calculator to actually go through and solve this problem for the angle where if I did tangent, it would give me 4/3. And so by using my calculator, so let me grab that out. Let's see. Make sure that your calculator is in degrees because we're measuring this again in terms of physics. And so application-wise, we're going to measure this always in terms of degrees. I'm going to do inverse tan of 4 divided by 3, and I get 53.1 degrees. So we'll just round to the first 10th degree here. And because this is angling towards the northeast in that first quadrant, this would essentially be 43 degrees measured north of east. So I need to make sure I say that. And then here is my direction. So we have our vector now defined in terms of its length and its direction. All right, example 2. So if a vector is based off of its measurements in terms of length and direction, is it possible then to look at vectors or alter a vector and what happens when we're comparing some vectors? So for example 2, sketch a new vector v that would still have a length of 5, but it would have a different direction. So if I wanted to change its angle, but maintain its same length, its same magnitude. So how might you do that? Well, one of the easiest ways to actually go through and do this is if I just want to change its direction, I just want to change which way it's pointing. I also don't even need it to be at the same starting location. So for example, I could start it here at the origin, and instead of going 3 steps to the right and 4 steps up, what if I went 3 steps to the left and then 4 steps up? Then this vector has a length of 5, but a completely different direction. I'm now pointing 53 degrees north of west. And you could apply the same technique by, instead of maybe going 3 to the left and 4 up, what if you went 3 to the left and 4 down? Or what if you went 3 to the right and 4 down and being in quadrant 4? So you have essentially 3 other options here if we want to maintain a length of 5 but a different direction. And so let's look at B, and then I'll kind of make a point here with that. All right, so B says sketch a new vector V that has the same direction but a different length. So what if I wanted to again maintain the 53 degrees north of north of east, but I don't want it to have a length of 5? What might that look like? All right, well again, what I can do is I can draw this vector. Now I don't have to start it at 1, 2. I can really start it anywhere I want, right? I could start it again here at the beginning. Well, if I want it to have the same direction but a different length, that means I just need to rescale that original triangle. So remember that the original triangle was a 3, 4, 5, right? It was 1, 2, 3, 1, 2, 3, 4. And so I had this triangle. Whoa, that's weird. So let's go here, 1, 2, 3, 1, 2, 3, 4. Remember, this was my original triangle here. And so I really just want this hypotenuse to change, but I don't want to change this angle. I want to maintain the similarity here. So I'm really just trying to rescale. Well, one way to rescale would be to divide everything by 2, right? So I could divide this by 2, divide this by 2, and divide this by 2, right? That would be the consequence. So this would say go 1.5 steps to the right, so 1.5, and then go 2 steps up, 1, 2. And therefore I would create a vector that would still have the same angle, but the length now is only 2.5 instead of 5. But if you were to do, again, inverse tan of 2 over 1.5, you should still get 53.1 degrees, meaning that the direction has not changed, but my length has. So notice that, again, the connection with trigonometry when it comes to vectors, that it's really just kind of rescaling triangles or trying to find the missing angle or trying to find the hypotenuse. And so you'll notice, again, one thing that I was kind of highlighting here in this example is that vectors aren't necessarily unique, right? If I say that a vector has length 5, and direction 53 degrees north of east, you could really put that vector anywhere you wanted, right? The only reason I drew this vector in example 1 here the way I did was because I was told that I had this initial point, 1, 2, and 4, 6, and then was asked to find the magnitude and direction. But remember that a vector is just drawn and just defined in terms of just these two things, meaning that the initial point can be anywhere I want. So generally in standard position, we always put a vector at the origin. And so that's what you saw me do here in this example 2. I said, all right, well, the easiest place just to draw this from is 0, 0. So let's just start there, and then I can walk off and count the points. So if a vector is defined that way, so again, just in terms of length and direction, I would encourage you to put it at the origin. It's the best place to kind of step it out and draw it. If, though, a problem tells you have an initial point and then you have to travel this certain way, then you have to draw the vector that way. At that point, it is unique and distinct in terms of its actual sketch. But just defined in terms of its distance and direction, so its magnitude and direction, it is not unique. If I was to take a vector and I drew this here and I called this u, this vector here is the exact same angle, so direction and magnitude as this one, which I could call v. Technically, these two vectors are the same because if I align them, they would be an exact match. So they're not special, right? They're not distinct. The only thing that makes them distinct is in terms of their initial point, but the vectors themselves are the exact same. All right, and so that's why it's really, really important that we have a standard if we're not going to define their initial position. All right, throughout the rest of this lesson, though, standard position isn't going to be a major highlight. In other words, you're just going to see sketches of vectors where you can put them however you would like to. It's just going to be based off the grid that you see on your screen and the grid on Notability that I'm using. And then we'll measure everything off of that. Okay, so let's take a look now at example 3. And this is what I was kind of talking about with the vectors r, s, and u. So determine the magnitude and direction for each vector below. Just to let you know, the scale, each square is worth 1 unit. All right, so if I want to go through and I want to find the magnitude and direction for each vector, we're essentially drawing right triangles, and I'm looking for either A, the hypotenuse, and then B, the angle. All right, the angle created by the horizontal. All right, so let's go through and let's try and solve for R. So let's do, we'll just kind of call this A. All right, and I want to do R, so I'm going to just kind of copy and paste my vector down here so I have it available. Let me make sure it's in the right corner. It's not, there we go. I want to make sure it's lined up because it's going to be equal. It's not going to be off. And just whole numbers so we can count it. So in terms of this vector here, I'm going to draw my triangle with the horizontal. So like this. I'll even get rid of the arrow so we can kind of see it. The angle that I'm looking for is right here. And so in terms of the magnitude, this would be 1, and this would be 1, 2, 3. And so the length, the magnitude for R, is equal to the square root of 1 squared plus 3 squared. Well, this would be the square root of 1 plus 9, which is square root of 10, and this is good. We don't need to go through and approximate this. Square root of 10 is exact. We don't have to get around a number. This is perfect. All right, what about for its direction? All right, so direction, I'm going to be doing inverse tan of opposite over adjacent, which will be 3 over 1. And then again, I'm going to use a calculator to do this. So I need to unlock, I'm using my phone, so I just need to unlock it. All right, and so I'm going to do inverse tan of 3 over 1, again, in terms of degrees, and I'm going to round to the nearest tenth. This will be 71.6 degrees. And notice, because I'm pointing northeast, I'm going to say north of east, because this 71.6 here is measuring that angle here. I'll kind of highlight it right there. And that's it for A. So this is what I'm looking for. So try B and C, which is S and U, respectively. All right, so for S, I'm just going to copy it over Make sure it lines up exactly on the dot. All right, now notice what's really weird about this one is I can't really draw a triangle for this, right? If I'm looking for the magnitude, don't make your life harder on yourself. Notice that this magnitude, if I wanted to try and look at it as a triangle, it would be all adjacent, right? It'd be 1, 2, 3, 4, 5, so 5 squared, plus there's no run, right? There's no opposite, there's no going up at all. There's no rise. Sorry, I said no run, but there's no rise. And so I'm solving this kind of problem here. Well, this just comes out to be square root of 25, or just 5, which makes sense again, because if we're just looking at the length of this vector, because it's aligned in terms of just traveling to the right, we could just count the number of units and get its overall length, right? We don't have to walk through and do this process. We could just say 5. Now, in terms of direction, this part is a little tricky because it's going to the east here. It's essentially 0 degrees, right? It's the positive x-axis. We can just say due east, though, because again, we're doing vectors. We don't have to give an actual degree measurement for this. We can just say due east. And so this is true if vectors are going north, west, or south as well. If there's no angle, you would just say due north, due west, due south, or due east, respectively, like we did here. All right, for C, so vector U. All right, hopefully this will fit down here, so I'm just going to kind of copy it over. Yep, okay, cool. All right, I'm going to draw my triangle. Now notice how when I draw it, this is traveling to the right, and then it's traveling down. So I'm going to draw my triangle like that. My angle is always created with the horizontal here. And so then I can kind of count in terms of how far I move to the left. 1, 2, 3, 4, 5, 6. And how I move down. 1, 2, 3. Now notice because I'm talking about left and I'm talking about down, I'm going to go ahead and put in a negative there to help give a sense of that direction. And we're going to talk more about this. You can actually see it on the bottom of the screen. This is referring to its component form. I will define that a little bit in a second. All right, but again, I'm really just worrying about what's the magnitude, what's the length of this vector for u. Well, this means I'm just doing Pythagorean. So I'm going to take the square root of a squared plus b squared, so negative 6 squared plus negative 3 squared. Again, be careful with these negatives that when you square them, especially in a calculator, the answer should be positive. So 36 and 9. This would give you the square root of 45, which is equal to 3 root 5. Because 45 is 9 times 5, I can take the square root of 9, which is 3, but I can't square root 5, and therefore we get our answer 3 root 5. So there's my exact length. All right, for direction, again, I'm doing inverse tan of opposite over adjacent, so this would be negative 3 over negative 6. Notice this is just doing inverse tan of 1/2, which is approximately 26.6 degrees, rounding to the nearest tenth. And because this would essentially put me in the third quadrant, if you think measured off the horizontal, this would be measured as south of west. And there's my direction. All right, and so here's how we can find magnitude and direction for vectors, especially when it's given to me graphically. Now, if I want to talk about these vectors algebraically, and notice that as I'm drawing out and doing this, I'm always referring to how a vector is traveling horizontally and how a vector is traveling vertically. Well, those are called components. All right, so when I want to talk about a vector, I can actually describe it and write it algebraically as component form. Now, it's listed essentially with these greater than and less than signs here, but they're exaggerated, so they're really, really big like this. So it helps show you that it's not an ordered pair. So you got to be very, very careful with this. They're not parentheses. What the first part here says is just like how X is all about a horizontal, how far to move right and left, A refers to the horizontal component of a vector. From its initial point, how far to the right do you travel until you get directly below your vertical? B then represents how many steps up or vertically that you need to get to your final position here. And then your arrow is drawn as the hypotenuse that would connect those 2 points. So it's very similar to if I asked you to plot a point on a coordinate and then draw the line from the origin to that point. That line that I would ask you to draw would be your vector, and its component form could be given by that coordinate because we're starting at 0, 0. All right, so when we look at something like this, notice my definitions then become a little bit more algebraic in terms of magnitude and direction. So for magnitude, for example, if I'm trying to find the length for V here, which is the hypotenuse of this right triangle, this would be equal to the square root of a squared plus b squared. And if you recall, and if you look back at the previous example, that's exactly what we were doing. We were taking the square of the horizontal and the vertical components, adding them up, and then taking the square root of that result. This would give you the length of V every single time. So this now kind of keeps you from having to draw the vector as long as I have the vector in component form. Now for direction, it's always going to be opposite over adjacent. So if we're putting the angle in the correct spot, this means we have this relationship that tangent of my angle is b over a. That would be my opposite over adjacent in the triangle that I've got sketched here. Well, because we're solving for the angle, theta is therefore equal to inverse tan of b over a. And then based off of what quadrant we are in, which the components would describe that, I could then know if this is north of east or north of west or whatever. And we can go through and answer from there. All right, and so we have this definition then, we have this new way to write a vector in terms of its components instead of sketched or given an initial point and terminal point. All right, and so one thing that I kind of want to point out, and I mentioned this, is if we were to look back at example 1, remember that was a vector v where we were told that we had an initial point of 1, 2, and we had a terminal point of 4, 6. All right, and so if I want to go through and actually express v in component form, I would need to know what its horizontal and vertical components are. So go back and look at example 1 and tell me what's your horizontal component. So how far to the right are you moving from your initial point? And how far up are you moving for its vertical? Well, looking back, its horizontal component would be 3, and its vertical component was 4. Recall that it was a 3, 4, 5. Positive 3 means moving to the right. Positive 4 means moving up. Now, notice this right here would be my change in x values. It's 4 minus 1. And then this vertical component was found by doing 6 minus 2, my change in y. So another way to essentially look at the component form is that it is your run, right, in terms of slope. So your change between your x2 and x1. And then your rise, which would be your change between your y values. This is another kind of formula that you can use specifically when talking about your initial and terminal. Now, you're not going to see this a lot, but it could be applied. If you move on again into a calculus class, so AB, BC, Cal 2, Cal 3 in college, you will see these formulas a lot. So I'm really just kind of introducing them to you. Again, we're not going to use this that much in terms of the scope of this class. All right, and so the next example I have for you is going to deal with these component forms. All right, so sketch the following vectors written in component form, and then find each vector's magnitude and direction. All right, so let's go through and let's try to do A. So A, all right, I've got V is equal to 2, 4. So then its magnitude is found by doing the square root of its horizontal component squared plus its vertical component squared. And then now I just need to solve this. So this would be the square root of 4 plus 16, which is the square root of 20. Now I want to reduce this. 20 can be split into 4 times 5. Square root of 4 is 2. Root 5 stays root 5. There's my magnitude. The direction is found by doing inverse tan of b over a, so 4 over 2. And the inverse tan of that would be 63.4 degrees. And because this is a positive 2 and a positive 4, this would put me in quadrant 1. So this would be measured as north of east. All right, part B. All right, I've got W is equal to the vector 0, 3. So its length, its magnitude, would be given as a squared, so 0 squared, plus b squared, which was 3. This would give me square root of 0 plus 9, which is just 3. And this makes sense because if you try to visualize this, notice how I have no run, only rise, right? This is only going up 3 units. I'm not moving to the right at all. So that means my direction would have to be due north. I could get that from its sketch by sketching this and traveling 1, 2, 3, but only going up. V, because I forgot to sketch this a second ago, would be 2 steps to the right as my horizontal component, and then 4 steps up. Here's a vector for V. Okay, for C, we had U is equal to -3, 5. So if I was to sketch this, I need to pick my initial point. I'm going to be taking 3 steps to the right, so 1, 2, 3, and then 5 steps up. 1, 2, 3, 4, 5. So the vector U can be represented geometrically like this. Its magnitude would be given as the square root of -3 squared plus 5 squared, which would be square root of 9 plus 25, which is the square root of 34, which cannot be reduced. Its direction would be given as inverse tan of 5 over -3, which is approximately, and the calculator, what you would get is -59. Now we only care about the actual 59 degrees. Its 10th decimal would be rounded to 0, and this would be measured as north of west. And this is what I meant, again, if you were to go back and look at the inverse function video, the reason why we're getting a -59 there is talked about in that video. We are, again, only concerned with the positive because that 59 is my reference angle. So all we care about is the actual number. We don't care about the sign of it. And that's true for cosine, etc. But we're always doing inverse tan here, sorry. All right, D. I have the vector -5, 0. So if I sketch this, starting with my initial point here, this would be 5 steps to the left, no steps up. So 1, 2, 3, 4, 5. So immediately I know what my length is. The length of this vector is just 5. I don't need to go through and walk through the format. And then my direction would be due west. I don't need to say 0 degrees. You could describe this as 180, but we're just going to say due west because that tells me exactly how we should travel. All right, so that's it for that example, and then this will move us into the next topic here, which is another way to rewrite vectors. Okay, so the next thing I wanted to look at was unit vectors. So a unit vector is a vector that has magnitude 1. In other words, it is a vector that has a unit length. So whatever that unit may be, 1 foot, 1 meter, 1 inch, 1 centimeter, 1 millimeter, whatever. So anytime I describe a unit vector, that is what I'm discussing. So all the vectors that we've essentially looked at so far have not been unit vectors because their lengths have been greater than 1. All right, and so when we talk about unit vectors, at the very core are 2 very special unit vectors. That is the horizontal unit vector, which is I, and its components would there be 1, 0. So in other words, you are only taking 1 step to the right, so therefore its length would be 1, and it's strictly horizontal. Then we would have a a vertical unit vector, which is labeled as J, and this would have the components 0, 1. It would be the vector if I was to draw due north and take 1 step. Now here is why these horizontal unit vectors, I and J, why they are so important. And this is going to really kind of lead into the next video, which is operations on vectors. In the sense of, let's say that I had a vector V whose component form was the 3, 4. It's something that we've seen a lot. And so if I wanted to sketch it, if I started here at the initial spot, and I was to go 1, 2, 3, and then 1, 2, 3, 4, and draw my vector for V, notice even how I did this as I went through and said, okay, well, this is 1, 2, 3. In other words, notice that I'm taking 3 I's to walk out this vector. And then in terms of my vertical, I went through and said 1, 2, 3, 4. In other words, I took 4 j's to create this vector. And so, in other words, I have 3 i's and 4 j's. So I can represent V as 3i plus 4j. This is essentially what I call unit vector form in terms of writing the equation for a vector. You can call this the standard form, but it's essentially written in this way. Now notice that if you have a vector that has component form A, B, then its unit vector form, or its kind of standard form, is written as A, I plus B, J. So it's another way to kind of write out the form, especially in terms of an equation. And notice that we're essentially adding two vectors, and we're also multiplying vectors. This I here and this J are individually their own vectors, right? 1, 0 and 0, 1. And I'm multiplying the first one by 3 and multiplying the other one by 4, and then we're adding the two together. Well, we haven't even talked about how we can do that, why we can do that, and what that even looks like. And so that's, again, what we're going to get into is how do I work with these vectors. But hopefully this kind of makes sense in terms of this format. So if we were to look at the vectors below, just practicing this definition here, write each of the following vectors in ij form. If you had a vector for vector A, which was 6, -2, it's pretty easy to see that this would be written as 6i plus -2j, which I can then really just write as 6i minus 2j. It's actually intuitive and is actually true to write it this way. Then if I wanted to do 0, 2, this would be 0i plus 2j, which is just 2j, right? The 0i means 0. I'm not going anywhere horizontally. And so 0, 2, which would be a vector that's going due north 2 units, that would make sense then that its vector in ij form would be written just in terms of j, right? I'm taking literally 2 j's to get up there. All right, now if I wanted to do C, a vector C, which is B minus A, all right, this is going to essentially introduce the next topic, which is C -2 minus 0, 2. If I was subtracting these two vectors in terms of their components, intuitively you would imagine that would this not just be their x's and their y's subtracting? In other words, it's always about like components. And the truth of the matter is that's correct. This would be 6 minus 0, or 6, -2 minus 2, which is -4. So C's component form is 6, -4. We're going to talk about this in the following video. And therefore, I can write the ij form for C, which would be 6i minus 4j. All right, and so unit vectors in the ij form, it is very, very important for future math classes. So again, this is just more of an introduction. In terms of the scope of this class, I'm mostly going to assess you in terms of component form. So recall that for a vector, its component form is given by a comma b, where a is its horizontal component, and b is its vertical component. Think about it like slope, that this would be the run, and this would be the rise. When this is the case, if I was to sketch at my starting position and draw my vector, A represents this distance here, B represents this distance here, which means a vector has magnitude and a vector has direction. If we define the direction by being always with the horizontal, then magnitude would be Pythagorean, a squared plus b squared, square rooting that result. And then the angle can be found by doing inverse tan of b over a. All right, here's that closure in terms of how to go through and find these vectors of what we discussed. Being able to find the components and being able to sketch given an initial point and terminal point. All right, so make sure to take a look at the practice problems. You will have a discussion post that you need to do for this lesson. And then if the project assessment is up, you can begin to look at that project assessment and start attempting that. There will be a video that accompanies it. So make sure to watch that video if you want to get some of the foundational knowledge. But it is definitely possible to go ahead and do the project without watching that video. So I would almost encourage you to do that and kind of challenge yourself. And then you can always look back at the video to get the necessary information to solve that problem. We have a virtual class on Thursday, which we'll go over basics of vectors as well as identities. I feel like we will primarily discuss identities during that class, but if you want to talk about vectors, make sure to bring that up, and I'll be more than happy to work through a couple problems with that. So thank you for watching, and again, contact me if you have any questions.